Hi everybody, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. And for the last five lessons I've been talking about cardinal numbers, which is section 5.4 of volume 1. And today I'm going to actually talk about bigger. I already talked about finite cardinal numbers. Those are pretty basic, just the number of elements of a finite set. That was my first lesson in this section. And then the last three lessons have all been on infinite cardinal numbers, but they've all been the same size. They've all had cardinality aleph null, which is the smallest infinite cardinal number. But it actually turns out that there are even bigger infinite cardinal numbers than aleph null. As a matter of fact, there's infinitely many. And Georg Cantor actually proved that there were infinitely many cardinal numbers. But I'm jumping the gun by mentioning that. Today I'm just going to talk about one larger one, namely the continuum. Anyway, let's begin. So the continuum is the cardinal number of the real numbers. And the reason it's called the continuum is because unlike the integers or the counting numbers or the natural numbers, if you like, those are a discrete set. It's what's called countable, because you can kind of list all the elements or count all the elements. You have to count to infinity. But you can't even do that with the real numbers. It's a continuous set. So, it's not obvious that there's more real numbers than rational numbers, but there are. And I'm actually going to present a simple proof of that fact. And that proof is what's called Cantor's diagonal argument. It's a very powerful proof. It's a proof by contradiction. And it's not even really that difficult a proof. I'm going to give it today. So how can we prove that there are more real numbers, say, than counting numbers, natural numbers, 1, 2, 3, 4, 5, so on? Well, I'm gonna give a version of Cantor's diagonal argument, but not to the real numbers themselves, but to just the real numbers on the unit interval. In other words, the interval from 0 to 1. So we're only going to continue real numbers that are strictly between 0 and 1, and actually less than 1. So they're on the interval from 0. Usually people write that with a closed bracket on the left, meaning it includes 0, but it doesn't include 1. Or I guess it could include 1 if you want. I don't think it makes that much difference. So we might as well include 1. So how can we show that there's more of these numbers on the unit of interval, more of these real numbers on the unit of interval than all the counting numbers? And when I say all the counting numbers, I mean up to infinity, 1, 2, 3, 4, 5, so on. Well, let's assume otherwise. I'm going to do a proof by contradiction. So whenever you do a proof by contradiction, you always have to assume the opposite of what you're trying to prove. So here, I'm going to assume that there's the same number of real numbers on the unit interval from 0 to 1 as there are counting numbers, 1, 2, 3, 4, 5, so on. If that was the case, there would have to be a bijection from between the counting numbers and the real numbers on this interval. That means we should be able to list all the real numbers on the unit interval. So we have to imagine that we have such a list. And I just started with a small list here. These are actually pretty famous real numbers. They're the fractional part of some famous real numbers. First one I think you recognize is just pi, but I'm starting it with 0 instead of 3 because I'm taking the fractional part. Remember that all these numbers have to lie in the unit interval between 0 and 1. So I'm just subtracting out the 3, and then you get 0.14159, 26535, and so on. All these real numbers, the decimal expansions all go, infinitely many far. These are decimal expansions, by the way, and you can represent every real number by its decimal expansion. And it could be rational or irrational. It could terminate. And if it terminates, we have to kind of use a convention here. There's actually two ways you can represent a terminating decimal. The usual way is you just terminate the decimal. And you can think that after the last decimal digit you wrote down, all the decimals after that are 0. But it's also equal to the same thing if you made the last digit 1 less and then just replace the zeros by 9s. I'm not going to prove this, but it turns out 0.99999 repeating is actually equal to 1. It's kind of a counterintuitive fact, but it is true. You'll just have to take my word for it. So the only rule I'm going to use for representing these real numbers on my list is that we're not only allowing infinite strings of 9s. If you have an infinite string of 9 at the end of your decimal expansion, just replace it by an infinite string of zeros and add 1 to the digit right before. So that's how you get rid of the infinite strings of 9. So I think you can see that every rational number between 0 and 1, or every real number strictly in the unit interval, has a unique decimal expansion of this form. And I've just written down 5 of them. I just said the first one is the fractional part of pi. Second one is a fractional part of e. E is probably the second most famous irrational number, irrational constant. I think I talked about E briefly in chapter 4. So it has a couple names. It's called Euler's constant, or the base of natural logarithms. It starts with 2. And I'm not going to say what it is because I do in that lecture, but E is approximately 2.71828 and again, like pi, it goes on forever. And since I'm only looking at fractional parts, I subtracted out the 2. So that's the second number on our list. Third number you may recognize. This is the fractional part of the square root of 2. Square root of 2 starts with 1. And again, I'm subtracting out the 1. So x3 is just 0.41421, 36523, and so on. That one goes on forever too. All these numbers I list are irrational. They don't have to be irrational. They could be rational, but all the ones I'm listing are irrational. Fourth one on my list is the golden ratio. I believe I talked about that one in chapter 3. That actually has an analytic expression. Square root of 5, 1 plus square root of 5 all over 2. And it's a very important mathematical constant. Again, that one begins with 1. It's 1.61803, 988, 39887, and so on. And again, I've subtracted out the 1's fractional part. Last number on my list is actually less than 1. It is already in this interval. And this one is the natural logarithm of 2, which happens to be approximately 0.69314, 71805, and so on. So these are just 5 irrational numbers on my list, but I'm assuming I have an infinite list, a list of every real number from 0 to 1. Okay, well now I'm going to apply an argument called Cantor's diagonal argument to prove that no such list exists. I'm going to get a contradiction. I'm actually going to construct a number that's not on this list. A number from 0 to 1, a real number from 0 to 1 that's not on the list. And it's actually a pretty simple procedure. So how do we do this? Well, let's look at the first digit after the decimal point of x1. That's 1. Now I'm going to add 1 to that. That gives us 2. And I'm going to keep doing that. So for the x2, I'm going to look at the second decimal digit after the decimal point for x2, and that one is also 1 because it starts out 0.71. So I'm going to add 1 to that. That's going to give me another 2. So now the new number I'm going to construct as 0.22, so on. Let's look at x3. The third digit of x3 after the decimal point is 4. I add 1 to that. That gives me 5. So now we get 0.225. And then the fourth decimal digit of x4 after the decimal point is 0. So I'm going to add 1 to that, so give me a 1. And the fifth decimal digit after the decimal point for x5 starts at 69314, so that's 4. So I add 1, that gives you 5. So now our new number is going to start out at 0.22515. And if I had infinitely many real numbers on my list, I could get infinitely many digits. And one thing I forgot to tell you, what if the digit is 9? Well, then just wrap around, make it a 0. It doesn't even really matter that I'm adding 1. I could just make them any different digit. But just to be consistent, I'm adding 1. So you can see the D starts out, like I said, 0.22515, so on. But I'm imagining I have an infinite list of numbers on my list. So we're going to get a decimal, we're going to get a rational number. You can see this. You're going to get a real number between 0 and 1. And I'm going to claim that this number D is not on my list. No matter how big my list is, it's an infinite list, I'm claiming that D is a number that's not on the list. How do I show that? Well, the first decimal digit is different from the first decimal digit of x1, so it's not equal to x1. The second decimal digit is not equal to the decimal digit of x2, so it's not equal to x2. The third decimal digit is not equal to the decimal digit of x3, so it's not x3, so on. I think you can see that the nth in general, the nth digit after the decimal point of D is not equal to the nth decimal digit after the decimal point of xn by construction. So it's not equal to any of these numbers xn, therefore it's not on the list. That is the essence of Cantor's diagonal argument. Pretty beautiful argument. I think it's a really beautiful proof. And it proves that there's no bijection, because that was our assumption. We came up with a contradiction. There's no bijection from the counting numbers, the natural numbers, 1, 2, 3, 4, 5, so on, to the rational numbers between 0 and 1. That means there have to be more. Why are there more? Because it's an infinite set. There have to be at least as many since it's infinite, and we know that the counting numbers is the smallest infinite set. If you like, you could take a subset of the real numbers. You could just say the first real number is 0.1, the second one is 0.01, third one is 0.001. I mean, there's a lot of ways you can do that, but you can obviously come up with a one-to-one correspondence between the counting numbers and a subset of the real numbers between 0 and 1. Since we have a subset that's bijectively equivalent, but it doesn't have all the elements, and we just showed that there's no bijection of the whole set, that means the whole set, the set of real numbers from 0 to 1, has to be bigger. It's a bigger infinite number. And we give it a name. We call it C. You might wonder why we don't call it Aleph 1. Well, the Aleph 1, by definition, is the smallest. It's the next cardinal, infinite cardinal number after Aleph 0. You might wonder, I mean, we just showed that C, the continuum, is bigger than Aleph, no. But is it the next one? And this question is known as the continuum hypothesis. And I think I should back up for a second. I forgot to mention one thing. We showed that the cardinality of the unit interval, the real numbers in the unit interval, is equal to C. What about all the real numbers? Well, it turns out that's also equal to C. You can actually show there's a bijection from the real numbers on the unit interval from 0 to 1 to all the real numbers. That might seem like a weird result, but it's actually pretty easy to prove. You can prove it by projecting the unit interval onto the entire interval. Anyway, you can just trust me. I'm not going to prove it here, but it's pretty easy to prove that there's the same number of real numbers on the unit interval from 0 to 1 as there are all real numbers from minus infinity to infinity. We call that the continuum, C. So, for a long time, mathematicians were curious whether or not C was equal to Aleph 1, whether it was the next infinite cardinal number after Aleph null. In other words, are there any cardinal numbers, infinite cardinal numbers strictly between Aleph 0 and Aleph 1? Well, actually, this is a very interesting question. It was very difficult to prove. There were a lot of mathematicians who tried to prove it but failed. But then there was, I think, the first guy who proved that it was consistent. He didn't prove that the continuum hypothesis, this is called the continuum hypothesis, by the way, the assumption that there's no cardinal numbers, infinite cardinal numbers between Aleph and 0 and C, I think the first person to prove that that was logically consistent, that the continuum hypothesis was consistent with conventional set theory, was none other than Kurt Gödel. He proved this in 1940. Kurt Gödel, in case you're curious, he's a very famous mathematician. He actually proved that he proved it was called two versions of what he called the continuum. What was it called? I forget what it's called. The Gödel's incompleteness theorem. Very counterintuitive result. It says that mathematics is either incomplete or inconsistent, and nobody believes it's inconsistent. So the result is that it's incomplete, meaning that there are true statements in math that can't be proven or disproven, but can be stated. Very counterintuitive results. As a matter of fact, it was kind of a shock to a lot of mathematicians at the time, because I'm digressing now. I'll get into this in volume 2 of my book, but I'm not going to get into it here. But anyway, he did, among other things, Kurt Gödel proved that the continuum hypothesis is... I think I'm jumping the gun here, by the way. I should be doing this in the next lecture. And I'm going to talk about the continuum hypothesis in this lecture, but just to suffice it to say that I'll just since I already jumped the gun, I might as well continue jumping the gun. It turns out there was another logician in the 1960s. I believe it was I forget his name. I wrote it down here somewhere. Paul Cohen. In 1966, I believe, he proved that it was also consistent with the conventional set theory that the continuum hypothesis is false. So you can't prove. This is a weird result. But it turns out that it's impossible to prove or disprove with conventional set theory the continuum hypothesis. You have to assume it as another axiom. Either assume it or you assume it's converse. But I guess there's just one more thing I want to say here. We proved that the continuum is bigger than Aleph null, and since it's bigger, another kind of weird result is that that all the real numbers are either irrational or irrational. And I think yesterday I proved that the cardinality of the rational numbers is also equal to Aleph null. That's a pretty counterintuitive result, but it was pretty easy to prove. We proved it with that square spiral. So if the cardinality of the rationals is Aleph null, and we can call the cardinality of the irrational numbers k. We don't know what that is, but we know that Aleph null plus k has to equal c, because c is the cardinality of the real numbers. Well, k. Let's assume that k had the irrational numbers had the same cardinality as the rational numbers. Well, then we would have Aleph null plus Aleph null, which is 2 Aleph null. And I think I proved also that 2 Aleph null is equal to Aleph null. And that's a contradiction because c we already proved was bigger. That means that k has to be bigger than Aleph null. As a matter of fact, it turns out k is equal to c. The cardinality of the irrational numbers is the same as the cardinality of all the real numbers. So there are more irrational numbers than rational numbers. That's another pretty surprising fact, I think. And this would have blown the Greeks away, because the ancient Greeks, remember, how they drowned Hippasus at sea for even proving that there do exist irrational numbers. He proved that the square root of 2 was irrational. And the Pythagoreans were so upset about that the legend is that they drowned them at sea for that discovery. So they didn't even believe there were any irrational numbers. Well, now it not only turns out that there are irrational numbers, but there's actually more irrational numbers than rational numbers. So rational numbers are the norm among the reals. Irrational numbers are the norm among the reals. Rational numbers are the exception. So I thought I'd just finish by mentioning that kind of counterintuitive fact. So you get a lot of weird results when you deal with infinite sets and infinite quantities. But it's pretty beautiful. That's why mathematicians love infinity, like I said, and physicists tend to hate it. But anyway, that concludes my video for today on the continuum. Thank you for watching. Long live math, and I'll see you guys next time. Bye.